Hi, it's Mr. Benson here with another video on the 2011 motion questions. Now I'm going to try and get through these faster so that I can have them up for you to look at very quickly. This is the first half, roughly 11 questions, averaging about 2 marks each. You're looking at 20 minutes work. Hopefully the video will be shorter than that. Okay, so moving on. When I get into the right screen, here we go. So our first question, we've got a racing car traveling around a corner at a constant speed. Now we're told a bunch of stuff. It forms a circle of radius 50 meters. So what's important here to recognize straight away is that we are talking about circular motion. We know R equals 50 meters. We know the mass. We know the force of friction between the tyres and the ground. Now when you're moving in a circle on a flat surface, the only thing that can be providing your centripetal force is friction between the tyres and the ground. So what this means is that this is equal to our centripetal force. So we know R equals 50 meters. We know the mass of the car is 700 kilograms. So all we've got to think about is an equation which relates all these quantities, and so we've got F equals mv squared over R. So all we have to do is substitute and then rearrange and then substitute. I'm going to rearrange first, so I get V equals the square root of FR over M. And then I'm just going to substitute in and solve what that is, so that we've got the square root of the force is 11,200 times 50 over 700. Then I'm going to get my trusty Casio FX82 calculator, and I'm going to work out what that is. So, well, I would if I could actually see the screen. Square root 11,200 times 50 divided by 700 equals, and I get 28.3 meters per second, or in fact 28 meters per second to two significant figures, which is sensible for this question. Moving on, what is the acceleration of the car as it goes around the corner? Now there's a couple of ways we could think about this one. But the easiest one is just to relate two quantities that we already know in one very simple equation. So we know that A equals F over M. Now we've already been told the force, it's 11,200. We've already been told the mass is 700, and so all we need to do is do that calculation. And we get 16 meters per second squared, which is quite impressive because that's faster than the that's more than 1 g of acceleration, but that's by the by. There is another approach to this question, which is that you can go back to your circular motion equation. So you could think about how A equals V squared over R. We know V, we know R, and we could do it that way. It's arguably a more complicated calculation. It'll get you exactly the same result, but I think what I've done is probably simpler. Okay, moving on. Two physics students are conducting an experiment, and we've got a block of mass 0.4 kilos, and all this kind of stuff here. Now, what we've got to think about in this question is what is moving and what is providing the force. Now, this is not an uncommon kind of question where you've got to think about those sorts of things. Now, because the blocks are attached, they are both moving and they're both going to accelerate at the same rate. So what we need to think about in this question is that the total mass is 0.5 kilograms. Now, the force is the weight on this block here, so that's W equals mg. So it's 0.1 times 10, which is 1 Newton. So we've got a force of 1 Newton accelerating a mass of 0.5 kilos. So A equals F over M. So 1 over 0.5, and it's 2 meters per second squared. I don't know why I left all that room. There wasn't much point to that. Anyway, next one. What is the kinetic energy of the block after it's travelled 1 meter? Now, there are, again, several ways you can do this, but there is one way that the examiners probably would like to see because it's the simplest one. And what you've got to remember here is energy transformation, so kinetic energy. Now, what's happening is that the weight force is doing work on the blocks, and so we've got the work that's done on the block will equal the kinetic energy. So KE equals work, which equals F, force times displacement. So we don't need to worry about fancy kinetic energy formulas. As long as we know the force and we know the displacement, then we're going to get the right answer here. There is one tricky bit to this though. When we're thinking about the force, it's got to be the force on M1 only. Now, when we have a look back at mass M1, that's a 0.4 kilo block. So the force on this block is given by MA because this Newton's second law always works for every object in a system. So if I want to find the force on block 1, it's going to be the mass, which is 0.4, times the acceleration, which was 2, so it's going to be 0.8 newtons. Then to find the work done, well, we know 1 meter is our displacement, 1 meter. So the work done on 1 is going to be Fx, which is going to be 0.8 times 1, so that's 0.8 joules. And this is equal to our kinetic energy. Okay, a circular motion question. So we've got banked corners, so this may be important. We've got some, now here's an important statement here. There is no sideways frictional force required. What that means is that the velocity of the bike exactly matches the angle of the banking. And so that means when we're working out angles, all we need to do is work out the angle between the two vectors, the centripetal acceleration vector and the weight vector. Okay, so what we need to think about here is the information we're given. We've got a radius, we've got a speed, and we've got, we've got the speed there. We don't have a weight, but we don't need it because we can just think in terms of acceleration. So moving over onto my blank page here. So the first thing, we know R equals 100 meters, V equals 10 meters per second squared. Okay, how embarrassing, meters per second. A equals V squared over R is our centripetal acceleration. So this is 10 squared over 100, which gives us 1 meter per second squared acceleration. So it's fairly gentle centripetal acceleration there. Now, when we're thinking about the angle here, well, let's think about our two vectors. Sorry, this is meant to be at right angles. We've got acceleration of 1 meter per second squared in this direction, and we've got the acceleration due to gravity, which is 10 meters squared in that direction, 10 meters per second squared in that direction. So our total acceleration vector is going to be on that angle, and then we can find the angle here. So theta is this angle here. Now again, you're always going to be using the tan ratio. So theta is going to be the inverse tan of the opposite, which is 1 over the adjacent, which is 10, and it's not going to be a very big number. Inverse tan of 1 over 10 gives us 5.7 degrees. Okay, the following question relates to, now hang on, I think I've missed something here, sorry, I just want to, right, I have, my apologies, I missed question 5. Draw two arrows to show the two forces acting on the bicycle and the rider treated as a single object. Now, what they're asking for here is the is not the centripetal force, because the centripetal force is the sum, if you like, of two other vectors. So what we've got to think about here is the forces that are actually acting on an object. So we have gravity, which is acting down, or weight, acting downwards. Now the only other force which is going to act on them is the reaction force of the track. Now that always acts perpendicularly to the track, unlike my terribly drawn one there, and it should also be somewhat larger than the weight force, because there needs to be a horizontal component to the vertical one, which is in addition to this vertical component. Actually, look, I'm starting to waffle on here, don't worry about that. I have drawn this a little too tall. Let me just scribble that, get rid of that. That's about right here. What it should look like is that the vertical height of this arrow above the point where the bike wheel is touching the track should be the same as the height of the weight arrow going into the track, because those two vertical components cancel out, and the horizontal component of the reaction force is what gives you your centripetal acceleration, or your centripetal force rather.